On April 17, 2025, NASA stunned the world with evidence hinting at a 99.7% certainty of life, at least as we know it, might exist not on Mars, but 124 light-years away on K2-18b. The detection of a rare gas linked to biology rocked astronomy and ignited fierce debate. Was this the first sign of alien life, or a cosmic false alarm? The story behind life on K2-18b is far more complicated and controversial than anyone expected. So how did a distant dot in Leo become the planet everyone is watching now? In 2015, a faint dip in starlight caught the attention of the Kepler mission team. Kepler's sensitive detectors, trained on thousands of distant suns, recorded a subtle but regular dimming from a red dwarf in the constellation Leo. This pattern, tiny reductions in brightness occurring every 33 days, hinted at a planet passing in front of its star, briefly blocking a fraction of the light. Astronomers call this a transit, and the depth of the dip revealed something surprising. The planet, soon named K2-18b, was about 2.6 times the size of Earth. The discovery set off a flurry of activity. Kepler's raw photometric data suggested a planet, but confirmation required more than a single instrument's view. Follow-up observations began. The Spitzer Space Telescope, using infrared light, watched for the same periodic dimming. At the same time, ground-based telescopes measured the star's slight wobble, Doppler shifts in its spectrum, caused by the planet's gravitational tug. Each line of evidence reinforced the case. K2-18b was real, orbiting its star at a distance where temperatures might allow liquid water. The planet's size and orbit placed it in a rare category, a sub-Neptune in the habitable zone of a cool, dim star. For the Kepler team, the confirmation was more than just another data point. It was a signal that even small, faint stars could host planets with the potential for life, and that the search for habitable worlds was just beginning to yield results. K2-18b stands out among exoplanets for reasons that go beyond its discovery. With a radius 2.6 times that of Earth and a mass estimated at 8 to 9 times greater, this world fits a category known as sub-Neptunes. These planets are too large to be rocky like Earth, but smaller and less dense than our solar system's ice giants. K2-18b's orbit, just the right distance from its cool red dwarf star, places it in what astronomers call the habitable zone, where temperatures could allow water to exist as a liquid. This combination of size and location immediately drew scientific attention. Sub-Neptunes are common in the galaxy, but few sit in the habitable zone, and even fewer are close enough for detailed study. K2-18b's bulk properties suggested a thick, hydrogen-rich atmosphere, raising the possibility that it could support a global ocean beneath its clouds. In 2019, the Hubble Space Telescope detected hints of water vapor in its atmosphere, making headlines around the world. For the first time, researchers had evidence of water on a planet orbiting another star, one that might even be temperate enough for life. These findings made K2-18b a top target for the James Webb Space Telescope's powerful spectrographs. Astronomers hoped that by analyzing starlight filtering through the planet's atmosphere during transits, they could decode its chemical makeup. The prospect of finding not just water, but other molecules linked to habitability pushed K2-18b to the forefront of exoplanet science. For many in the field, it became the planet to watch, a rare chance to peer into the atmosphere of a world that, on paper, seemed almost too promising to ignore. To probe the atmosphere of K2-18b, astronomers relied on 3 main instruments aboard the James Webb Space Telescope. Each plays a distinct role in capturing the planet's secrets. NIRSpec, the near-infrared spectrograph, covers a range from 0.6 to 5 microns, targeting the wavelengths where water vapor and methane leave their fingerprints. NIRIS, the near-infrared imager and slitless spectrograph, operates in a similar band, but with a design that excels at tracking subtle changes in starlight during a planet's transit. Both instruments collect time series data, sequences of exposures taken as K2-18b passes in front of its star, allowing scientists to watch the atmosphere's effect on starlight in real time. MIRI, the mid-infrared instrument, extends the reach further, capturing light from 5 to 28 microns. This mid-infrared range is crucial for picking up molecules that are invisible at shorter wavelengths, including certain organics and sulfur compounds. By combining the data from NEOSPEC, NIRISIS, and MIRI, researchers assemble a spectrum, a detailed map of how the planet's atmosphere absorbs and transmits different colors of light. Each instrument's cadence, or timing of exposures, is carefully chosen to catch the fleeting moments when K2-18b's atmosphere imprints its chemical signature onto the incoming photons. Behind the scenes, teams of engineers and scientists calibrate every detector, correct for instrument drift, and piece together the raw data into spectra ready for interpretation. The result is a layered record of photon counts and wavelengths, a foundation for decoding the planet's atmospheric chemistry. The next step, translating these patterns into a list of molecules and searching for the fingerprints of life. Retrieving the chemistry of K2-18b's atmosphere begins with the spectrum, a pattern of light and shadow carved by molecules as starlight passes through the planet's upper layers. Each molecule absorbs light at specific wavelengths, leaving behind a set of fingerprints. In the case of K2-18b, the James Webb Space Telescope's instruments picked up broad, unmistakable features in the near-infrared and mid-infrared ranges. The most prominent belong to water vapor, with strong absorption bands around 1.4, 1.9, and 6.3 microns. These are the same wavelengths where water in Earth's atmosphere makes its presence known, and the match in K2-18b's data is striking. Methane, a much simpler molecule, imprints its signature at 1.6, 2.3, and especially 3.3 microns. The retrieval algorithms, mathematical models that fit theoretical spectra to the data, lock onto these bands, adjusting the abundance of methane until the model lines up with the observed dips. Carbon dioxide, with its distinctive 4.3 micron feature, rounds out the major players. Each of these molecules requires a different set of conditions to form and persist, so their coexistence in the atmosphere of K2-18b is a puzzle with far-reaching implications. The process is iterative. Scientists test their fits by subtracting the model from the data and examining the residuals, the leftover signal. If the model accounts for all the features, the residuals should look like random noise. When unexplained bumps or troughs remain, they hint at missing chemistry or unmodeled molecules. In this way, the routine mapping of water, methane, and carbon dioxide becomes the foundation for deeper questions about the planet's true nature. A curious feature appeared in the mid-infrared spectrum, a pronounced absorption bump that did not match the expected fingerprints of water, methane, or carbon dioxide. This anomaly drew the attention of the retrieval teams, who pored over the residuals, the difference between the observed spectrum and the best fit model. The excess absorption centered near 9.3 microns stubbornly resisted explanation by known atmospheric constituents. As models cycled through possible molecular combinations, one candidate began to fit: an organosulfur compound, specifically dimethyl sulfide, or DMS. On Earth, DMS is almost entirely produced by marine microorganisms, rising from the oceans in quantities that shape our planet's climate and cloud formation. The presence of a DMS-like signature in K2-18b's atmosphere was both electrifying and unsettling. In the data logs, the fit improved dramatically when DMS was included, reducing the unexplained residuals to near the noise floor. The absorption strength suggested an abundance nearly 20 times higher than Earth's atmospheric levels. For the team, this raised the stakes. DMS is considered a prime candidate for a biosignature gas, a chemical beacon that, if confirmed, could point to active biological processes. Yet the implications demanded caution. The mid-infrared is home to many overlapping features, and the possibility of unknown or poorly catalogued molecules could not be dismissed. Within hours of the initial fit, emails and chat threads among the analysis team captured a mix of excitement and skepticism. Some researchers urged a conservative approach, pointing to the need for independent verification and the risk of overinterpreting a single spectral feature. Others, seeing the sharpness of the DMS fit, wondered aloud if this was the first real sign of extraterrestrial life, a moment that could redefine humanity's place in the cosmos. The debate was far from over, but the organosulfur flag planted in the spectrum of K2-18b had already transformed a routine analysis into a scientific drama. Confidence in the detection of dimethyl sulfide on K2-18b hinges on more than just the data itself. The numbers that make headlines, like the 99.7% figure, are shaped by the assumptions built into the statistical models. In exoplanet science, Bayesian retrievals are the standard. These methods start with a prior, a mathematical statement of what is plausible about the planet's atmosphere before the new data are considered. A prior can be broad and agnostic, allowing any abundance of DMS, or it can be narrow, based on what is known from Earth or laboratory chemistry. When the JWST team analyzed the K2-18b spectra, their original retrieval used a mildly informative prior, subtly steering the solution toward biogenic scenarios. This choice sharpened the posterior, a probability distribution showing how likely different DMS abundances are given the data, producing a sharp spike at values consistent with life as we know it. Switching to an uninformative prior, which places no preference on biogenic or abiotic origins, flattens the posterior. The apparent confidence in DMS drops, and the Bayes factor, the statistical measure comparing the evidence for DMS versus no DMS, can fall below the threshold for a solid detection. For example, under the original settings, the Bayes factor for DMS was reported as 17.5, translating to roughly 3 sigma, or 99.7% confidence. But when the retrieval code is rerun with a wider suite of molecules and a log-uniform prior, the Bayes factor can dip to 2.3, well below the standard for a claim of discovery. These shifts are not just technical details. They reveal how much the result depends on the model's starting assumptions. The statistical story told by the data is not fixed. It bends and flexes with every tweak to the prior, every added molecule, every change in the noise model. For scientists, this is both a strength and a caution. Bayesian inference makes the uncertainty visible, but it also means that confidence is always conditional, never absolute. Within weeks of the NASA announcement, independent research groups set out to verify the claims about K2-18b's atmosphere. Teams at institutions like the Space Telescope Science Institute and the Jet Propulsion Laboratory downloaded the public JWST spectra and began their own retrievals, eager to see if the dimethyl sulfide signal would hold up under fresh scrutiny. Each group brought different tools to the task. Some used the PLA-TON retrieval code, while others rebuilt the molecular line lists from scratch, expanding the roster of candidate molecules far beyond the original suite. Where the first analysis had focused on water, methane, carbon dioxide, and DMS, these reanalyses included sulfur dioxide, hydrogen sulfide, and carbon disulfide, along with other trace gases that could leave overlapping marks in the spectrum. The results were sobering. As the list of considered molecules grew, the apparent strength of the DMS signature faded. Bayes factors, a measure of how well the data supported the presence of DMS compared to models without it, dropped sharply, in some cases falling below the threshold that scientists use to claim a detection. When uninformative priors were applied, which made no assumptions about the likelihood of life, the statistical confidence in DMS shrank even further. Some teams reported that the DMS spike in the posterior distribution flattened out, replaced by broad, ambiguous curves that could be explained by noise or by other molecules. Instrumental effects added to the uncertainty. In 2024, a memo flagged a previously uncorrected artifact in the NIR spec detector that could mimic or exaggerate spectral features near the critical mid-infrared bands. Pipeline developers rushed to patch the reduction software, but questions lingered about whether the original DMS signal was partly an artifact of the instrument. The combination of expanded molecular lists, neutral priors, and detector systematics left the community with a more cautious outlook. The initial confidence in a biosignature had been eroded, not erased, but tempered by the rigor of independent checks. Sulfur-bearing molecules like dimethyl sulfide, long considered a hallmark of biological activity on Earth, have recently been traced to entirely non-biological origins elsewhere in the cosmos. In 2016, the Rosina instrument aboard Rosetta identified dimethyl sulfide in the coma of comet 67P/Churyumov-Gerasimenko. No living organisms exist in these ancient icy bodies. Yet, dimethyl sulfide was present, formed through chemistry driven by cosmic rays and ultraviolet light acting on frozen mixtures of methane, carbon dioxide, water, and sulfur. This cometary evidence points to a pathway for dimethyl sulfide production that requires no biology at all. Laboratory experiments have since recreated these results under controlled conditions. In 2024, researchers exposed comet analog ices, combinations of hydrogen, methane, water, carbon dioxide, and sulfur compounds, to ultraviolet radiation. The result? Measurable amounts of dimethyl sulfide and its close cousin, dimethyl disulfide, synthesized abiotically. These findings mirror the chemistry expected in the upper layers of hydrogen-rich planetary atmospheres, especially under the muted ultraviolet output of a red dwarf like K2-18. Photochemical models now incorporate these pathways, showing that trace amounts of dimethyl sulfide can arise naturally, even in the absence of life. Predicted levels from these abiotic processes typically fall far below the concentrations reported in K2-18b's spectrum, often by an order of magnitude or more. But the models also highlight a thorny problem. Spectral features of dimethyl sulfide overlap with those of other organosulfur molecules, creating degeneracies in interpretation. As a result, even a strong spectral match can be ambiguous, leaving open the possibility that what looks like a biosignature might instead be the product of exotic but lifeless chemistry. Pressure mounted behind closed doors as the April 17th deadline approached. In the Cambridge lab, the retrieval code repository ticked upward, dozens of commits in a single night, each one refining the models, patching corner case bugs, or tweaking the statistical priors. At 2:14 a.m. on April 15th, the final version locked in the now famous 3 sigma result for dimethyl sulfide. The internal chat logs reflected a mix of exhaustion and disbelief. Some team members urged caution, others pressed for immediate release. Arguments broke out over a single line in the draft press statement, whether to call the result life-compatible or to stick with the colder language of statistical preference. The morning of the briefing, the mood was tense. Scientists rehearsed answers to likely questions, anticipating the inevitable focus on the 99.7% figure. One lead analyst, running on little sleep, reviewed the code commit history on a laptop backstage, double-checking that every retrieval step could be defended in front of the world's cameras. In the press room, the first question from the floor cut straight to the heart of the matter. Does this mean you've found life? Panelists hesitated, then delivered a carefully worded response. The result was consistent with a biosignature, but not proof of life. Off microphone, the private debates continued. Some researchers worried that the headlines would outpace the science, that the nuance of model-dependent probability would be lost in translation. Others felt the weight of years of work riding on a single press cycle. For the scientists at the center of the storm, the release was not just a data point, but a test of integrity, balancing hope, skepticism, and the responsibility that comes with extraordinary claims. On April 17, 2025, NASA released data showing a 99.7% statistical confidence for dimethyl sulfide in K2-18b's atmosphere. This molecule, on Earth, is most often produced by living organisms, but laboratory and comet studies confirm it can also form without life. The evidence included detailed spectra from the James Webb Space Telescope's NIR-SPEC, NIR-ISS, and MIRA instruments, as well as Bayesian models supporting the detection. Yet, independent analyses revealed that confidence drops under different statistical assumptions, and possible instrument artifacts remain under review. The scientific community agrees that the detection is extraordinary, but the origin, biological or abiotic, cannot be confirmed with current data. Key details about atmospheric chemistry, surface conditions, and planetary environment remain unknown or classified. As of now, K2-18b stands as a landmark in exoplanet research, a planet where the line between life and chemistry is not yet clear, pushing us to refine our tools and methods for the next discovery.